All right, how we doing today, all? Good. Okay, so before we get into it, today we're going to use the whiteboard a bunch to talk a little bit about what's actually going on under the hood regarding how values are passed around to variables and functions. So if you can't see the whiteboard, you might want to move so you can see it. And before we do that, show of hands, how many attempted the Sudoku problem? How did that go? It went good. What does everyone else think? What about the grid? Like to get the subgrid?
Yeah.
Yeah, that's the hardest part by far. But if we have the rest of it to get a row, to get a column, to check if that's valid, and you have a bunch of really small, nice functions that the main function's pretty readable, then that's really good. And that's what I'm looking to see out of this problem, really. Because it shows that you can practice, making code pretty modular so you don't repeat yourself often. It's pretty readable, it's pretty flexible. If we were to change the size of the grid, how much code would need to be changed in your algorithm? That's another question. But in general, if you can get that down, then the entire problem structure is pretty good. And then you just have to worry about the subgrid, which is one isolated problem. And that one's a little bit trickier with some nested for loops, depending on how you set it up. But no matter how much you get done, you can send it to myself or Noel over Slack. Send us the link and we'll get feedback maybe by the end of this week, else by the end of next week for sure. So make sure you do that if you haven't yet. Cool. Any questions on the project or anything that we have covered so far? No, we're good.
Yesterday,
Yes.
there was a problem we did with Noel, and her solution was a little bit different than the actual solution, and it didn't work. But it was so close, and she didn't know exactly why it didn't work, so we were trying to figure it out.
Is that what she asked about in Slack today?
Yeah.
It is. Okay, so her solution was using that code that didn't work? Okay, so we will cover that in a few minutes. Let's build up to what's going on under the hood there. So we'll do a basic example of pass by value, then I'll show you how pass by reference works, and then we can look at why her code didn't work. Sound good? Cool, okay. So up here, we're looking at this example to start. Let me just comment everything else off. So up here, we've got a variable called str, and we initialize it with the string Chris. Then we make another variable, str2, and we assign it str. So we'll talk about what that actually does in a second. But then we go back to str, and we add on this z character. What do you think these two variables will hold when I run this program? Okay, so str, does it have a z? Okay, so we can talk about this better. I know my names are tough to talk about. Will str have a z in it? What about str2? That's correct, it won't. So let's just do on the board how this works. So remember that when the program first runs, JavaScript actually will look for all the variable definitions and pretty much throw them up here. They don't have a value yet because we haven't processed the actual lines that assign them, but these variables exist. Does that make sense? Cool, so on line 8 it says go to that str variable and give it this value, which is pretty easy. It's just a string right here. And so now what happens when we assign a variable to another variable? So it says, okay, we need to give str2 some value, and its value should be whatever the expression on the right-hand side resolves to. And how we resolve this lookup is we go to the scope and we say, what is the current value of str? Oh, it's this string Chris. So we basically plug in that string Chris. And at this point, str2 has nothing to do with the original str anymore. It just looked at like a snapshot of what it was at that time and said you should be the same exact thing that is right now. And now they both have the same value, but they're not really the same variable in memory anymore. They're totally separate. They just have the same values. So on line 11, we say, hey, we want to modify that variable str. It should actually be equal to itself plus z. So really, it's going to do the lookup. It's going to say, okay, this is what it currently is. This is plus z. Smashes them together. And now the updated value of str is this. Nothing had anything to do with str2 on that line. So this is the current state of our global scope. And so when we run that out, it'll look like the whiteboard. Does that make sense? Cool. So let's look at how this works with complex data types. So real quickly, what are some complex data types in JavaScript? Objects, arrays, functions. That's it. What are the primitive types? Boolean, string, number, undefined, null. Yeah. So for all primitives, they're going to follow the example we just saw. When they get assigned a value, we look up the current values of all the other variables, and we plug in those values. And whatever value we smash together at the end of that expression, that's what the new variable takes. But those variables really have nothing to do with each other than when they're plugged in for that one formula when we assign it. Does that make sense? Cool, so now let's look what actually happens on line 18. Again, we said, hey, we want to make some space in memory for something that's called nums. And now when we actually hit this line on 18, and we hit this bracket operator, we're telling JavaScript, hey, I need you to go make some space in memory for a complex data type. And in JavaScript, these arrays can be any size. It doesn't know if we're going to hold just one element inside of there, or if we're going to hold thousands of elements. That's part of the reason this works a little bit differently. So as soon as we hit that bracket, or if it was a curly brace, or if it was a function, behind the scenes, we're telling JavaScript, I need you to create a complex data type. And when it does that, it acts a little bit differently over here. It says, oh, I need to make some space in memory to store whatever you're going to put inside of this thing. So you can imagine that somewhere else behind the computer, there's something that's called the memory pool. And it's kind of like your RAM. It's the memory that all of the programs run inside of, or store the data that they're going to use. We say, hey, go in memory, get me the first available address, and reserve me a chunk of memory to store this thing. And so what that looks like is, over here we have a visual representation of a memory address. So like standard is that if you ever see like binary or references to memory addresses, we'll usually denote it with this 0x. That's all it means, is that this is a place in memory. And then to the right will be some number that signifies where. So we're just going to make it simple and always be like 0 or 1 or 2. And the 0x just means, hey, this is a memory address. Does that make sense? Cool. So it says go into memory, and at this memory address, whatever you find, I need you to make some space for this array. And it's going to say, okay, here I can store the array with the numbers 1, 2, 3. And so this all happens as soon as we have these brackets here that say go create an array. And as soon as it actually creates the array, it comes back and says, hey, I made that thing. And this is where you can find it. So the variable nums actually holds a reference to where the data in the complex data type actually exists. Does that kind of make sense, even though this is kind of conceptual? You can't ever really see this happening under the hood. So the variable that holds a complex data type actually holds a reference, whereas the primitives held a value. So now when we say, hey, nums2, I want you to take whatever the current value of the variable nums is. Well, it works similarly to how it did before. We're going to say, okay, so nums2, you should be whatever nums1 is. And we look on the scope, we say, oh, nums, that's a reference to this memory address. So you should also hold the same exact reference. So we just take that exact reference right here. So now on line 21, whenever we access a variable that holds a reference, we say, hey, go to nums. And JavaScript says, oh, okay, it's this reference here. So this is the thing that I'm actually about to work with. It says, at that memory address, I want you to push in the number 4. So we come over here, we update in memory, and we add that 4 to that memory address. But did this variable change? So the variable here didn't changed. The variable is still memory address 0. We didn't really do anything with the variable. We just went through the reference and modified the actual data behind it. But the variable wasn't reassigned at all. So there's a difference between totally reassigning variables and mutating the data that's inside of their references. So that kind of makes sense.
Yeah, the same reference, yes.
Yes, but nothing changed on the scope list, right? We didn't actually change the variable. We changed the data that this variable was referring to. And that's what the push method did. So now, on line 22 and 23, when we run this, what array do we expect to come out? The first array we expect to see 1, 2, 3, 4. What about the second one? The same thing, yeah. So on line 22 and 23, when we say, hey, go look up that thing num, so on 22, it says, oh, it's memory address 0. Let me come over here. This is the thing you want me to log out. We log out 1, 2, 3, 4. Then for nums2, which is a different variable, we say, oh, this is a memory address. Let's follow this memory address. This is the thing that I want you to log out. So they look exactly the same. And so now, if we said is nums triple equal nums2, what do we expect to happen? True, yeah. So one motherfucker. Hello? Well, this is weird. Not sure why the scope wasn't populated here. I don't know if anybody saw that, but after it ran the program, I should be able to log out nums. And so I don't know what broke there. But we see here now, if we log out, is nums the same as nums2? The only thing that really happens is it looks at both of these variables and says, oh, this one's a reference, this one's a reference, and they're the same reference, so they must be the same. It doesn't actually look inside of here. So that's why, if we did this, what do we think will happen now? False, yeah. So basically what happened is we created nums. We went to the first available memory address. As soon as we come over here, we have that bracket, right? It says, hey, I need you to create a complex data type. So we go to the next available memory address, and we also put in an array of 1, 2, and 3. And when we created this, nums2 would instead take what as its reference? Yeah, memory address 1. And so to the human eye, it looks like they're the same. Here, those are both arrays that have the same values in them, but they're not the same array. So when we compare them, it sees, oh, this is a reference, but they're not going to the same place in memory. That's all we care about. They're not the same. It doesn't actually look at the values inside of there. Because we want to know, are these the same exact thing? If I mutate one, will it reflect on the other? So in this case, if we push 4 into nums, what do we expect to happen now? Exactly. So on line 21, we say, hey, follow nums, memory address 0. Come to this thing, put in a 4. Is nums2 changed? No. So then later, when we say go log out nums and nums2, we follow both their references, and these are the things that get logged out on the screen. So that was pretty fast. That's the general overview of how this works. Questions?
So if they do share the same memory address, you know how we just use num.push 4? If we use num2.push 4, it will also be the same. It goes both ways.
Yeah, so in the case, you mean going back to this, right? Yeah. So it doesn't matter what variable we go through. It doesn't know how we assign them. Just at this point in time, both nums and nums2 are references to memory address 0. Does that make sense? So it doesn't matter which one we go through because nums2 evaluates to this reference. So when we follow this reference and we mutate this thing, well, if num still holds the same reference when we go to look through nums, this is the current state of the data. Yeah.
And so you're saying that for the primitive types, they just hold the exact value to begin with. So there's no middle memory address for the primitive types.
Exactly. Primitives, if you reassign it, you reassign basically only that one. You can't modify both of them with one equal sign. There's no link between them. And here the variables aren't really linked either. It's more so that the variables both got instantiated to the same memory address. So anytime we go to that memory address and make changes, anybody who's watching the same spot in memory will see those changes. So to illustrate that a little bit better and get to what I think part of the problem was in Noel's example is, okay, what do we think will happen here? I just added line 22. Reassign nums. So what do we think is going to get logged out for nums and nums2? Okay, so let's visualize this. So after line 20, this is the state of our scope, right? Nums is memory address 0, nums2 is memory address 0, and we pushed into that address. Well, when we reassign a variable, it doesn't affect the old data that variable was at. We're saying, hey, go reassign nums to whatever this thing on the right-hand side is. Reassign the variable. So it comes over here, it says, okay, I'm putting a new value in for nums. It's whatever this is. This thing is the number 10. So variable nums is now the number 10. We didn't operate on that memory address. We had nothing to do with it. We said this variable should now just point, or not even point. This variable should just hold this value now. Did we do anything to nums2? The variable. Did we do anything to this memory address? No. So now when we go to 24 and 25, it says look up that variable nums. What is it? It's the value 10. We log that out. It says look up the variable nums2. Oh, that one's a memory address, so let's actually go over here, grab this thing, and log this out. Questions? Yes.
Are you able to actually return if something has a memory address, or what the memory address is?
So everything I'm doing on this whiteboard is how it works under the hood, and JavaScript doesn't expose any of that to you. In other what we call lower level languages, you actually have to manage the memory yourself. So then another good example would be, well, what happens if we say nums2 is now equal to 100? So what am I going to change on the global scope? So nums2 is no longer, the variable nums2 is no longer holding that reference. It's now 100. And so this is where JavaScript is smart. It says, hey, I'm holding this thing in memory, but literally nobody has a reference to it anymore. You can't ever get this again. JavaScript is smart like that. It says nobody can ever access this thing. So why am I holding it? What happens? Garbage collection. Says, let me go clean up the memory that nobody can see anymore because you can't use it. And it's gone. Other languages like C++, you have to know, hey, I have to go back and clean up that memory space because nothing can access. Otherwise, you'd have a memory leak. And if you have a bunch of those in your code, the program's going to get slower and slower the longer you run it and ultimately eat all the RAM on your machine. JavaScript doesn't let that happen, as long as you know you're not still pointing to data you don't actually need. So that's kind of what happened under the hood there and how the references get cleaned up. No variable held a reference to it, You can never see it again. Questions?
To clarify, you're saying that example 1 on line 8 would, it's a simple issue, so it wouldn't actually generate a memory.
Yeah, it's a primitive data type. JavaScript can just hold that value paired with that variable name, so to speak.
So why is it, like, if you're referencing that string 2 is equals to string, and you're saying that the string is Chris, you're saying that it wouldn't be modified? Line item 9, so 9 isn't modified by.
So 9 isn't modifying anything. The English here is saying, hey, give me variable str2, and its value should be whatever str currently is. So str currently is the string Chris. We should also be the string Chris, but they're different. It's just used to like initialize it. And if it was a complex data type, we'd look up and we would see, hey, that variable is pointing to a spot in memory. So I should also point to the same spot of memory. I should hold the same memory address. But the variables themselves aren't linked. It's more so that if you go to an address that multiple variables can see, when you read from any of those variables, you'll see mutations. But a reassignment of a variable doesn't go back and change any variables that you initially took a value from, if that makes sense. There's kind of a difference between assigning the variable and actually setting or modifying some data. Do we? Yes.
So complex, basically you store in memory pool. When it's not complex, you're just storing in global pool. I mean global stuff.
Yeah, so that's how we're going to think about this. Yes, JavaScript is doing some memory management under the hood to how to figure out where str actually is, but this is the concept of how it's working. We don't have to go really under the hood. We can pretend that the variable literally holds a primitive value, or it holds a reference to where the complex data type actually lives. That's the way to think about it. So let's see, how does this work with different scopes? So take a second to look at this code and try to imagine what's going to happen on the whiteboard using our knowledge of functional scopes. So it's just this example. We've got this function pushes4. We create a variable called other nums. We call pushes4 with other nums, and then later we want to log out whatever other nums currently is. Yeah, so this one's not going to be too different than what happened before, but basically, out on the global scope, we create a thing called other nums. I'm just going to leave it as nums here. As soon as we call line 36, we say, hey, we want to run a function. What happens? As soon as we call a function, what does JavaScript kind of do under the hood as it relates to scopes? Okay, so we found the function, we called it, yeah. Now we want to run the function. What's going to change up here? We make a functional scope, right? Like a nested scope. So like if I declared something inside of this function, it would only exist while we're inside of the function, right? It's not going to be on the global scope. And so as soon as we create a functional scope, it also declares variables that we've defined as the parameters to the function, right? Regardless of if they're passed in or not. So as soon as this happens, we're saying we need to create something called R, and this is going to take whatever value is given to us as the first argument down here. Let's review, does that make sense? So in this case, how does that work? What value are we going to give to R? It's going to be whatever other nums is, right? So we look, what is other nums? It's not actually 1, 2, 3. What is the variable? The variable itself is holding, whoops, it's a reference. That variable is currently pointing to a complex data type. It held a reference. So when we say, hey, R, you should be whatever other nums is, we look at other nums and it's memory address 0. So we're saying, hey, R, you should look at memory address 0. Kind of makes sense?
Yeah.
So now, when we're inside on line 32, we say find that thing called R. We find it on our functional scope. It's currently memory address 0. We follow that to go over here, and we put in value 4. Now the function ends. What happens on the whiteboard? Garbage, yeah. As soon as the function's done, we get rid of that functional scope. And now back out on the main scope, we're trying to log out what other nums is. Has this variable changed? No, the variable is still the same memory address. We didn't reassign the variable at all. But when we log it out and we follow that memory address, this is what's currently inside of it. And so we'd log out 1, 2, 3, 4. And that's how references get passed around. So like as soon as we initialized R and it took the memory address 0, the variable R doesn't have anything to do with the other nums variable anymore. It just said, hey, whatever you are, I want to do the same thing. So it was the same memory address, and then we just used R to modify the memory pool. So later, if another variable was still pointing to the same spot, whatever changes we made have persisted. Questions?
So it still points, just to clarify, it still points to the reference pool. The memory pool, we're using the reference, and then if you make the modifiers to it, it points to it.
Yeah, if we actually access through that reference by doing something like push, it's saying follow that reference, now on this thing is where I want you to push. We modified the data that the references point to, but we didn't really change the variables.
Right.
We have to begin to think like that a little bit, that variables are kind of different than the data that the variable holds, or the reference that the variable holds. So we can only, when we have that equal sign, we're really reassigning the complete variable. We're not actually modifying the old data that that variable pointed to. Which is why in the earlier example over here, reassigning the variable didn't actually go and modify how the arrays looked. It just meant, hey, this variable, you're no longer looking at that array. You should just give out the value 10 when somebody accesses you. Cool, so we'll take a quick look at the code from Noel in Slack, and then we're going to move into slides and do 10 more of these examples, and it'll start making sense. And if you feel overwhelmed, that's okay. This is a weird topic, and it's kind of different than how you might expect things to work so far. And it's not like we sit here every day and draw this out on white paper every time we're trying to solve a problem. This is going to become natural for you, and you'll feel that something's off if you're sharing references and you didn't want to, or you'll know when you want a new reference. And it'll come back to that idea of mutating data that we spoke about when we introduced some array methods. What's an array method that mutates data? What did you say? Splice does, but what did you say?
It said slice.
Slice does the opposite. Okay, so let's do slice real quick then so you have an idea. Okay, so we've got other nums, which has 1, 2, 3 in it. Okay, I'll just leave this pushes for here. That way the whiteboard is still correct. So the whiteboard is correct right now. Now we're saying we need a new variable called new nums, and it's going to take whatever this expression on the right spits out. So under the hood, we implemented slice, right? What was the first thing you did inside of slice? Okay, so take a step back. What does slice do?
It's a section.
It gives us a section of an array, yeah?
So it has a starting index and an ending index, and it basically cuts out or makes a copy of a slice of an array starting at that index and ending at that.
Yeah, with slice, basically the definition is, hey, we want a new array that has all the values the old array had, but in between these points. And so when I call slice with no arguments, what am I saying?
The whole thing.
Get me the whole thing, right? So when we implemented that, the very first thing you did inside your function is what?
Or find a memory address.
Yeah, you create a new array, right? Then we set up a for loop where we went from the start index to the end index. We accessed the old array value and we put it in the new array. And at the end, you returned a new array. So while we don't see that we're creating a new array right here, that's what slice is doing under the hood, and you implemented it like that. So what slice does is it says, hey, I need a new spot in memory, and I'm going to hold an array. And we said go from the start to the end. So it looks at the old one. It says, hey, I need this value, this 1. I need a 2. I need a 3. I need a 4. And when it's done, it kicks back and gives us memory address 1. And that's what we save as new nums. So if I log these both out right now, to the human eye, they're going to look like they're the same. But they're not the same because what? They're different references. And so that's slice is an immutable method. It gives us back a new array, totally new reference, and that array will have whatever changes or mutations we want it to make without affecting the original memory address. What is this? So this is the example that she had here. We're just going to re-emulate this real quickly. So I'm just going to simplify this a little bit and remove the double nested array. Wait, board row number, never mind. That's correct. Okay, so we have a little bit of a Sudoku board here. All right, so as soon as I say board equals bracket, we tell JavaScript, make some space in memory to make me an array, right? But what is the first value of this array? It's another array, right? So if we're creating another array, actually, what am I going to do up here?
Create another memory.
Yeah, so we're going to make memory address 1. And this here is this inner array. So this thing is the one that holds 1, 2, and 3. What is actually at the 0th index of board? 0, 1, yeah, it's this reference here. So right now, board is a reference to an array that has one element. And that element is another array. It's a reference to another array. And that's where our 1, 2, and 3 are. So we haven't even got to the meat of her problem yet, but that's how nested complex data types are going to work. What's the only thing with a reference to memory address 1 right now? What? Yeah, memory 0. So it's a little bit of a trick question, but we don't have a variable that refers to that directly right now. Board instead holds memory 0, and memory 0 has the reference to 1. So if we ever delete board, JavaScript is smart enough to know, hey, this is the only thing that referred to this, and it'll delete them both. But that's an aside. Okay, so now let's just go all out with this example. We got 2 more variables, right? We've got row and we've got column, and they're both the number 0, right? Are they the same number 0? No. But are those variables equal? Yeah, because their values are the same. Okay, so on line 48, we're saying we need to make a new variable called spot. And spot should be the result of this entire expression. So to start this, we say, hey, go find board. Board is memory address 0. So this is the thing that we want to work with. And in board, we need to plug in row number. So we look up, row number is 0. We take 0, and we say, okay, we're going to the first element of this board. So that's this. So far, board and row num evaluate to this pointer, to memory address 1. Does that kind of make sense? This is like deep now. This is as hard as it gets. And now, because we've solved this, and we solved this, we have memory address 1 for this part of the expression. We're saying on memory address 1, plug in column number. And we look, column number is 0, and this is the thing we're working with. So when we plug in 0, what do we get? We get this number, this value, this primitive value right here. So we say, hey, spot, you should be what? You should be number 1. And so now, when we have spot on line 49, we're saying find that variable spot, completely reassign it. What's the only thing that's going to change on the board up here? Spot. Yeah, we're saying go to that variable. I don't care what you used to be. Spot had nothing to do with board anymore. Spot was just the number 1. And now spot is going to be the string value x. So reassigning spot didn't change anything over here. No. That's correct. So instead, let's look differently. How did this work? Well, here we're saying go to board, which is memory address 0, plug in the 0, which is memory address 1, and then we plug in the another 0, and it says this. This is the thing that we're reassigning. That's board, row num, column number. We just accessed it with all of that. This bit accesses it, and we're saying now we can reassign you. So in this case, this can become x. So we kind of see the difference between line 53 and line 49. Kind of. That's okay. As you see, other people that are developers also don't fully grasp how this is working. So it's okay to feel completely overwhelmed right now. We just want to start thinking about this, and it's going to get easier. I mean, I'm not putting Noel down, but apparently this was confusing yesterday. And so, like, to show you, it's okay to be confused, and you don't have to feel overwhelmed. But we'll break it down slowly, step by step, until this will start to make sense. But the big takeaway here is that Spot said, hey, you should be whatever is currently inside all of this. And that number was 1. So we gave the 1 to Spot, but it has nothing to do with this anymore. Spot's not like I'm always pointing to that spot. It's like, hey, I got a number back, that's all that I am. So if we reassign Spot on 49, we have to realize that this is just reassigning like a variable. That had nothing to do with going back and being like, oh, I need to go change where I came from. That would be so hard to follow. You think that you want that right now, but it would actually suck to code like that. So then on 53, instead, we went deep inside of a reference. And so while we were inside of there, we totally reassigned the data that was inside of it. And that was different than pulling that data out and giving it to another variable.
So it's not getting reference, that's why, right?
What's that?
It's not getting reference, that's why.
Yeah, spot wasn't a reference. Spot said I should be whatever was right here. I got the number 1. That's all that I am. That's all that I care about. It wasn't a reference. But here we actually followed through all the way into memory and modified what was in there. So later, if we go look at board again, we'll see that board now holds So here, after we reassigned spot, nothing changed on the board. After we actually went into the board, into the row, into the column, and we changed it to X, and we log out board again, that's when we saw the change happen. Yes?
So basically we can just reference anything that's above the absolute reference.
I don't know what that means. Well, I just don't want to say yes or no if I don't fully understand and give you raw knowledge. So can we reword the question?
So you know how when we create spot, if spot reference the absolute reference of the location on the board, then that is just not good. But you can reference the level right above it. As in if it reference the row or the column, that's okay.
Yes, okay, so let's do that example. So in this case, and I'm just going to simplify this and take out the extra variables now. What did we want to do here? Okay, so let's just leave it at this right now. So we created the board. This is what the board looks like. When we assign spot, what happens? So step through slowly. It says let's go to board. Board is currently memory address 0, right? So we follow over here. And we say go to the 0th of this thing. What's that? That's what? What?
It's an array, yeah.
It's a reference to the array, right? So we're saying spot, you should be that value, 0x1. Now what do we want to do? So to answer questions, I'm asking you, what do you want to see happen here? So I know where to take this. So spot is currently a reference to this array. So what do you want to see happen with your earlier question?
So like now it points to that memory address.
Yes.
And so like right now, if you perform a function on it, like spot bracket 0, that'll give you the 1 in the array.
Yeah, so let's look at 2 examples here. So let's do this one first. We're saying spot 0 equals x. What is happening? We look spot up on the scope, right? We get memory address 1, so it's this thing. We have no idea that this thing is inside board. We don't care. We just know that spot wants to modify this thing. So spot now says, hey, on that thing that you just pulled up, spot, go to the 0th index and make it an x. Right? Did this, what?
That's line 51, right?
Yes. Did spot change on the global scope?
No.
The variable is still pointing to the same spot, right? We just changed something inside of it. So now if we go log out board, board is still unchanged. It's still memory address 0. Still this array that points to memory address 1. None of that changed, but what's inside of memory address 1 changed. So if we log out board, we would see the X in it. What's the difference between 51 and line 50? So we go back to this state, and I'm saying I want to reassign spot.
It would replace the entire array with an X.
No.
It would create another reference?
No. Okay, so we're reassigning a variable. So we say we don't care whatever spot used to be.
It would replace garbage, no?
We're saying spot, the variable is now the value x. We didn't use spot's reference. We didn't go over to memory address 1. So we don't change this thing. We're saying that variable, I don't care that it used to be a pointer. This variable is now just the value x.
Because it's a primitive value.
Yes, we assign it to a primitive. We didn't like follow the reference there. We said the variable is totally reassigned. Whereas over here, we actually said follow that reference and go change the data inside of it at the 0th index. So board still has memory address 1 inside of it, and memory address 1 hasn't been changed. We just said, hey, we don't care what you used to be. You're now x. We didn't follow the reference. We didn't mutate any data. We just changed this variable. Board is unchanged. Yes.
So what's being referenced to it then? That.
So board is an array that holds one thing, and the one thing inside of board is the reference to this row. And this row, we didn't access this row. Spot used to point to that row, sure, but we said, hey, we don't care what you used to point to. You're now x. It doesn't actually go say, hey, that thing you used to point to, this should now be x. No, it's not like that. So it's a little tricky, but it's gonna make sense when we do some problems. But that's about as hard as it gets. We just have to go slow and think about it, that there's a huge difference between totally reassigning a variable and actually accessing the data inside of a reference and updating it. It's totally okay to be confused right now. This is fast. And we see that it's tricky to a lot of people, even after using JavaScript for a while. So don't let it get you down. All right, any questions on that before we go to the slides and do simpler examples again? Cool. So, pass by reference versus pass by value determines the behavior of how we assign variables. And it relates to if it's a primitive or a complex type, why? Because primitives the variable is just a value. Yeah, it's just literally a string x or some random number. But complex variables, they actually hold a reference to where the data actually is, which means multiple variables could point to the same spot. And any variable that follows the reference and mutates the data will be visible to all the other variables that are watching the same spot in memory. But with primitives, there's no way that I can update one primitive and somehow change a different primitive. I can only reassign one at a time. And when we're talking about mutation, like with pushes, we're not really reassigning any variables. We're just changing the data inside of the references. That's the big difference here. So this is mostly confusing as it relates to variable assignment, which we see as the problem right here. But we also saw how this works when we pass values into functions. How did we feel about that? We only did one example. It was the pushes for. It took in a reference to an array, then followed the reference and called the push method to mutate it. So that makes sense how that had its own scope. It had its own variable, but it took a reference from outside and then followed that reference to push. Equality operators, when we compare complex data types, what are we actually comparing? Yeah, we're comparing, hey, are you both referring to the same thing in memory? We don't care what's there, but if you're not referring to the same memory address, you are not the same. With values, we actually have to look at them. Do these strings have the same exact characters, so to speak? And this is really important when dealing with arrays. We need to now have in our head this concept of immutability. Are my variables pointing to the same exact array, or do I have a new reference? Because let's say that I hadn't, why we need to think about this is, let's say that somewhere I have the alphabet written out as an array. This is the alphabet. It should never not be A, B, C, etc. But later I might want the reversed alphabet. And so this is actually incorrect. Reverse isn't returning an array to me, but I might think that. What does reverse actually do? I don't know if we've used it or covered it enough, but do we have any ideas? Yeah. It does not create a new array. That's the problem. Here, we'll just do up here. So up here, smaller example here, we made an array called nums, 1, 2, 3. And we said, hey, go to that array and call the reverse function. And so it actually looks like reverse did return the reference to me. But if we go to nums, nums doesn't look the same as it did when I made it, right? Nums has actually been updated. So reverse mutates the array that you called it on. Which means here, I might think I have the alphabet and then the reversed alphabet. But really, reverse mutated the original alphabet. So instead, I have to know in my head, hey, I want this alphabet array to always be ABC. And then I want another array that is the reversed version of that. So rather than call alphabet.reverse, what do I have to do? Yeah, I need to say first copy everything inside of alphabet into a brand new array, because that array is the one that I can safely call reverse and keep these things separate.
So we should create a new variable and copy our alphabet.
Yeah, if we're wanting to make changes to an array but basically still have the original array, then we have to make a copy. And dot slice is the cheapest way to do that. So over here now, what is this going to be? False. Yeah, we got back a brand new reference. So slice basically returns a brand new array that looks the same. And on that thing is what we call a dot reverse. So that's where it becomes practical in real life, that we have to know, hey, is this going to modify the existing array? And is that okay with me? Or do I want basically both states of this array completely separate from each other? Generally, if I'm going to hold the alphabet and a reversed version, I probably want separate arrays to do that. If I want to instantiate the reversed one with whatever is in the original, well, dot slice is how I can do that quickly. So that's where this is really going to come into play. We don't have to draw nested references out all the time. It's going to become muscle memory, and we need to be aware of it, but it'll get easier, and you'll just have an itch to do this and not mutate the original. So that's kind of how it works in real life. Yeah, question?
Yeah, just to clarify, so if we don't use the dot slice method, we just create a new array equals to the original array, and then we perform.
Is that how it works, though? Is this? Goddamn. What actually happens here? Yeah. Yeah, it's going to be the same reference. So either of these that we call reverse on, we're only going to have the reverse version. This is not giving us a new array. This is saying reversed alphabet should point to whatever alphabet is pointing to if alphabet's a reference. If it was a primitive, then we would have two copies of the primitive, so to speak.
So to follow up on that, if we try to do an equality test on the
Right here?
No, on the previous one, on the alphabet. So alphabet, the array alphabet would be
dot reverse?
Yes, it would. Yeah, reverse apparently returns the same reference and it modifies the same reference. So let's just look real quick.
That's so tricky.
What's that?
So it's kind of fun. Like keep mutating it.
So this one is kind of all over the place to actually find the knowledge I was looking for. So up here it says the reverse method reverses an array in place. If you ever see in place, it means it's modifying the existing one. And that algorithm isn't using any new arrays at all, which makes it a little bit harder, but that's cracking the coding interview stuff. Don't worry about that. Anyway, the first array element becomes the last, and the last becomes the first. So far, I still don't have a clear idea of what array I get back, other than in place. I know it modified. And down here, it says it returns the reversed array, which is actually kind of tricky to read this, because that kind of makes it sound like you get a new array. But really, it's giving you back the same array reference that it just mutated. So I actually don't like the documentation here. But that is how it works, and so we could check it over here. So this is a shitty example because there's actually nothing to reverse here. But we do see that whatever comes out of reverse is the same exact array as num. And I mean, it would look different. They'd both now be reversed, but I only put one element inside. That wasn't the point. The point is it gives you back the same array. Yeah. Which it doesn't matter if it gives you back the same array because you already had that reference, right? So if you have this, you'll usually see just reverse completely on its own line because it doesn't matter. We still have the alphabet variable, which is the same reference. Yeah, question. So it didn't change any of the variables to give them new references, but it did follow the reference and go flip everything around in here. And then just spit back the same thing. It changes what's in the memory, yeah, but it gave you back the same reference you already had. So there's no new array being created. That's the main takeaway here. No new array.
Is that what destructive means? It mentions that reverse is destructive.
Yeah, where'd you see that?
In the comments.
Yes, that's what they mean. So generally, you'll probably see mutative more, but destructive, yeah, it means the same thing. It's going to fuck up whatever you had on that reference, and anybody that still has that reference will see those changes, and you can't get back to what it used to be. That's what it means.
Unless
So
you call unless you reverse it again, I guess.
yeah, but what was the point of that? Yeah, exactly. You're correct.
Is that using cryptography? I'm guessing that's like a function that would probably be used for cryptography. Cryptography, you reverse it and you flip it around even more.
I think you're thinking of like hashing,
Right.
which is we take one input, it runs it through some crazy algorithm that will always spit out a unique value. And so there'll be a one-to-one map of, hey, only this specific thing can ever create this specific thing. And so technically, in some forms of the algorithm, you might be able to take the output and run it through that algorithm reversed to get the original. But it's not this type of reverse at all, so everyone can discard that information. Yes?
I was wondering, if that's the case, so is the reverse function basically pushing the zero index to the array, and then popping shifting the first index out, and then just keep looping through it?
Yeah, so there are many ways that we could implement reverse. And I do like your way better, but probably most people's initial thing would be to say, hey, I'm going to start with a pointer at the end and a pointer at the front. I'm going to take this thing, put it in a temporary variable, take whatever was here, put it at the end, and then take the temporary variable and put it at the start. And then I move inwards. That's mostly how you're going to see it done. But I agree with you, it's easier to, rather than worry about that and all your indexes, why don't we just take off from the end, put it on the front, and keep track of doing it array length times. Again, if you don't keep up with that, that's totally fine. Not important. That's more algorithm stuff. Like if we were going to write, hey, write the reverse function in place, it's actually a job interview question that would be acceptable. We don't have to worry about that though, so let's continue. Good question though. All right, this we get by this point. The last addendum is that functions are also references, which I won't visualize right now, but you know complex data types. And that'll come up later when we pass functions into functions. We're passing a reference to that function. Overwhelming though, I know. Okay, so over here, let's get some confidence back. British city, we give it the string value York. And we say, get me new space for something called American city. And it should take the value that whatever British city is right now, which is what? York. So we have two variables. Both of them are the string York. Are they the same string? Like if I change one of the variables, will the other be changed? No, at this point they're done. They're both their own variables. They have their own value. So if we update American city, we say, I don't care what you used to be. You're now the result of new plus whatever you currently are, which is a little weird to think about, but that is how it works. And does that change British city? No. So we log them out. We've got York and we've got New York. Does that make sense? Do we feel confident about that? Good. Okay, we'll bring it back in now. Good. What?
It's back to confidence.
Good. All right. What about in this case? As soon as we see those brackets, what do we know is happening? Complex. So we would make some space in memory. British city is going to be what? So, okay, so stop saying that it's an array. The variable is actually a reference to an array. That's how we have to think about it. I'm not scolding you. I apologize if that sounded harsh. I'm trying to drill it into your head. Don't say that the variable is an array. The variable is a reference to the array. That's how we can have multiple variables point to the same spot. And that's why reassigning a variable doesn't actually change whatever it used to refer to. Just as this variable is no longer a reference, it's now whatever this is. Okay, so if British city is a reference, and we say American city is equal to British city, what do we have? We have two variables, and each of them are pointing to the same spot in memory. They have the same reference. So before I finish the slide, pretend that right after we said American city is British city, if I go and say British city equals 10, what happens? Yeah, are any arrays changed here? No, we just say British city is no longer that reference. It itself is now the number 10. That variable is the number 10. American city is still an array with York inside of it. Yeah, so that's a harder example than this slide, so just wanted to make that clear. So we go back, they're both references, and we say, follow American city. It's a reference. Let's go to that actual array, and let's unshift new. What does unshift do? Yeah, it's going to throw the new into the beginning of that array. So if we look at British city, has the variable been changed? No, it's still pointing to the same array that it's always been pointing to, but when we log it out, the array has been updated. Both of these have the same reference, and even though we went through the American city variable, they're both pointing to the same spot, and this is the only array that we have in memory, and these are its current state. Does that feel better a little bit? So why do they behave differently? You know, why is it? One, complexes, variables that are assigned to complex values get a reference. Primitives exist entirely independently. So now on these slides, we have a visualization of what I do on the board. So, whoops. We make a variable called first. It is currently the numeric value 20. Over here, we say we don't care what you used to be. You're now the value 30. And we say second, you're a new variable, you start with the value 30. And over here we say with second plus plus, it says go look at yourself, whatever number you are, increase it by 1, and you are now that number. So it was 30, 30 plus 1 is 1, second is completely, 30 plus 1 is 31, second is completely a new number, it's 31 now. Make sense? So we've got 30 and we've got 31. Okay, so now this time let's actually, instead of create them to different numbers off the bat, let's actually pass the value. So we say first, you're 20, second should be whatever first is. We look up, first is 20, so second should be 20. At that point, they have nothing to do with each other anymore. They both just happen to both hold the value 20. So when we increase second, we say, hey, second, your value was 20, 20 plus 1 is 21, second is now 21. First is completely unchanged. Make sense? So we get 20 and we get 21. That's passed by value. With complex, though, the variable doesn't store a copy of the value. The variable is what? It's a reference to where the array actually lives. The variable is not the array. So instead, the variable stores a reference in memory, and the reference points to where that array actually lives. So we create something called first. We have the brackets to make some space in memory. And the array constructor under the hood says, hey, that variable, you're holding this reference. This is where you should go to see the array. So when I say, hey, look up what first is this memory address. Let's go there. It's an array, so we can call the push function. Push mutates this thing to put in the 30. And now when we log out first, the variable itself hasn't changed, but when we follow through, this is the new state of that array. Good? In this case, same thing. We create an array. First available spot is memory address 1. It gets 10 and 20 inside of it. We create another array that also holds 10 and 20. Are these things triple equals? Are they double equals? No, double equals with complex is also going to look at references. There's no looking at the values. A little bit of a trick question. We didn't cover it yet. And in this case, they're both different references. So if we go through second and we update this memory address, nothing happened to the other memory address. Does that make sense?
Oh, sorry.
Yes.
So first and second, the equality is false.
Yeah. And visually, how do we know that?
Oh, we know visually because
Yep, because they both created arrays here. The brackets means go create a brand new array. So it doesn't matter if they look the same inside. They're not the same. They got created completely separately.
I think
Different references.
what about single equals?
What about what?
Are they loosely equal?
Okay, no, so loosely and double equal, loose and triple equal. With complex, it's still only going to compare references. That's it. That's better that way, honestly. Because we don't really care if you both held the same data inside. Why does it matter to us, really? Because if we change one, the other one's not going to be changed, and so they're not the same. Like, that's what we care about. It's changing one of these is going to update the other. That's why we want to know if they're the same array. We don't care if they look the same. You could write your own function to determine if they look the same, if that's something you need to do. What about in this case? Do we see the slightly different visualization over here that I can't really do on the whiteboard? How many arrays did we create? How many brackets you see? We created one. So there's one thing in the memory pool. There's one array. It's at memory address 1, and that's what first is. So when we say second, you should be whatever first is. First is a memory address right now, so second also takes the memory address. They're separate variables, but they hold the same memory address. So if we access through either of these references, everywhere else that has the reference will see those changes. So this time we go through second, it's memory address 1, we mutate this thing. So later, if we go through first, then it's still the same reference, it would see the updated change. If I triple equal these, what do I get? And if I double equal, what do I get? Exactly. All right. Ooh, our friend. What happens here?
We create a new array. Different references because we create a new array.
Different reference, but the elements inside are the same, which is important to know. I don't want to overwhelm you, but if we did have another array inside of here and we sliced, the inner elements would be the same reference. Slice only does this copy on the top level, so to speak. So I'll demo that later, but be aware of it for right now. So now we got back a new array. It started out with whatever values were in first, which was 10 and 20. But now the new one is a brand new memory spot. So when we go through this new value, this new variable, and we push, only the second array is affected. Does that make sense? Okay, well, if I accidentally exited, I'll show you one more thing that might help. Okay, so if we don't have the headspace for this, don't worry about it. But this is another thing in ES6 that basically means that we don't have to use slice anymore. And visually, this might help. So what we have here is we're saying create a brand new array. That's what the brackets are. The only new thing here is this triple dot. It's called the spread operator. And it allows us to basically spread all of the values that were in an object or an array into a new thing. And so how this works is it basically says, go find that array called nums, grab the 1, grab the 2, grab the 3, and spread them out inside of here. So this is the same exact thing as if I said nums.slice. If we don't have the headspace for spread, that's okay. But I think visually this helps represent that if we use slice or we use spread, we have a new array. Because those brackets are obvious there.
So, if it's a nested array, does it become a flat array?
No, it's only going to copy top values down. Same as slice. It works exactly the same as slice. Just this visualization might help. And then honestly, it's way easier to type this than to type slice. And on the eyes, it becomes more readable. But right now, it looks like more symbols, so it's not important. Just thought that you should know if you see it.
Using that's much more simple syntax, basically.
Exactly. Yeah. Right now, your head might be like, what are all those dots? But once you got used to it, it's way easier to spread things around than to call slice.
Right.
Cool. All right. So now we're going to pass variables into functions. We create a function called adds20. It takes in one argument. And on line 8, we call adds20 with whatever my num is. So we make a functional scope for adds20. We make a variable called num, right? And we say, num, your value should be whatever the thing is over here. And we look up, we see my num, oh, that's the number 10. Okay, so num is equal to 10. Num has nothing to do with my num anymore. So inside of adds20, we say go to our num. Num should be equal to itself plus 20. So num becomes 30, and we return num. So adds20 turns out the number 30, and we log out my num. Is my num changed? No, we can't do that with primitives. Oh, the answer was up there the whole time. Does that make sense? Cool. So what about this one? Hey, this is exactly what I did before class. We create a variable called myArray, and the variable itself is what? Reference to some array that has this 10 in it. So now, when we call pushes 20, it makes its own variable called array, and it says you should be whatever my array is. What is my array? It's a reference. So array is a reference to the same spot. So here on line 4, we follow the reference, and we throw a 20 into that array. And we return this variable, and this variable is what? A reference. It's the same reference that array was, but we capture the return value anyway as returned array. And so if we log out my array, it doesn't look like I changed that variable, right? Nothing happened with my array. But when we log it out, what's inside? Oop. It was there. They are the same. Strictly equal?
Yeah.
Yes.
Loosely equal?
Yeah.
They're the same reference, they're the same thing. That's correct. All right, we create two arrays, we throw the same exact stuff inside of them. They're equal, right? No, they're not. Brand new arrays, how do we know that? On 3 and 4, we both created brand new arrays with the brackets. They can't be the same. But here, how many times do I create an array? Just once. And the variable array1 is what? It's a reference. So when we say array2, you should be whatever array1 is. Array1 is a reference. Array2 is now the same reference. So strictly equal? Yeah. And if I go through either of those variables right now and I call some mutative method, both variables will see that because they're the same reference. Okay, this one we'll go back to the whiteboard for, but do we have a better feeling so far than an hour ago? Okay, cool. So this is about as hard as it gets again because we have the nested problems to deal with. So array 1, we say we need you to go create some space in memory, goes to the first available spot, which is memory address 0. So immediately, this is coming back to us. But what did we do inside of here? What am I going to put in right here? 0th index is what? 1. But what happens after that comma?
Another reference.
Yeah, I said you needed to go create me another array. So we go to the next spot. And what goes in this one? 2, 3. So that means that the second element of this first array is a reference to another array. But array 1 is just a reference to the top level array. So what happens on line 4? Yeah, so imagine inside of slice it says, hey, I need some new array. And it makes it. And then it says, let me go look at array 1, the thing you called me on, and I want to copy the values inside of there. So it says, oh, I've got a value 1, and I've got a value that's a reference. So it puts that reference inside, and it stores itself in memory. So the new array is down here. And it says, okay, I need to return myself. So it returns this new array that it creates. And that reference is what? Which one? This one, the one we just created, right? It looks the same, but Slice just created that. Gives it back. Are array 1 and array 2 equal? No, they're brand new references. But if I said, let's go to array 1, index 1, what value do I pull up? I pull this up. And if I say go to array 2, index 1, I pull this up, right? So is this the same as this?
Yes.
Yeah, those are strictly equal. Those are the same array. So Slice copied a brand new top level array, but it didn't do much more than that. And that could lead to problems if we're not aware of it. So if an array has a complex value as an element, only the reference to that complex value is copied into the new array. That's what they mean by this visualization here. The same reference got copied down. So that's why we say Slice makes a shallow copy. It only made a new array and then put all the same shit at the top level. That's it. So down here on line 10, if I said go back to that array 1, go to memory address 0, that's array 1. Go to the first index, memory address 1. This is the thing that I've selected. Like I think about these terms on the left as like selecting data. So we selected array 1, then we selected the first index, which is actually this reference. So this is the thing that we're currently operating on with dot. So we say on this thing, go push in 4. So now later, if I go back to array 2 and I go to index 1, I follow to here, and mine has been changed to have the 4 added inside. Does that make sense? If this makes sense, we're in a good spot because this is seriously as hard as the concept goes. It's just obviously, we're going to have more nested things that have 10 layers nested inside of them. Not in this class, but in real life. But the concept doesn't change. It's the same concepts at play. It's just that the data structures get bigger. And so we have to know, do I have to copy everything at every layer deep if that's what we're trying to do and have a totally immutable chain? None of that makes sense now. Don't worry about that. By the time you get there, this will be muscle memory.
What
Yes.
about with the index 0?
What?
No, array 1 at index 0, is it equal to array 2 at the index 0?
Yeah, so if we're looking at this and we're looking at this, they're not the same number 1. But when we compare primitive values, we say, is this the same data type? They're both numbers. They're both the number 1. So yeah, they're equal. But if I said go to array 2, go to the 0th, and make it the letter C, what's going to happen on my memory pool for this one? Think about what we're selecting.
That one will be
Yeah, so I'm saying select array 2, it's memory address 2. On this thing, go to the 0th index and reassign it. Did this affect mine up here?
No.
No, it didn't at all. Okay, so last one then, making this as hard as possible. If we instead said, go to array 2, go to the first index and reassign it, what's going to happen here? Think about it slowly for a second. So what do I select? I select array 2, and then I go to spot 1. This is what I'm operating on. And I reassign the spot in here. I'm not actually changing memory address 1. I'm just saying in this array, this spot is now a C. I didn't follow through to that whole thing up here and totally change anything here. I just said, hey, this array, you're no longer pointing there. Your first index is now the letter C. And so I guess I lied. This is probably as hard as it gets. And I think that comes back to the problem that we had earlier today in Slack. That was reassigning an index, which is kind of like reassigning a variable. We didn't go to that whole array and modify it. We just said array 2, at the first index, you're no longer a reference, you are now C. It didn't modify anything on the reference. But that's really tricky. That's okay if we don't get that part. If we get everything else on this slide, we're good to get started. Yeah?
If you were to change that to array 1 at index 1, would that have changed it to changing the reference at 01?
No, because either way, I'm saying on this array, so if I switched it back to array 1, saying on this array, I want to reassign what the first index is. And the first index is basically another variable. So we're just saying we don't care that this index was a memory address. We're just going to make it whatever we want. If I ran both of those lines of code, I changed first index in array 2 and array 1, does anything still have a pointer to memory address 1? At that point, it would get completely deleted. But we can't reassign this whole array. We have to access this array and change inside of it. We can't completely say, this thing is now a letter C. We instead said indexes, you no longer point to a reference, you're now the letter C. So that's a little bit of the difference with how the assignment operator works. That's okay, we can come back to that example. Yes?
Quick follow-up on that. So if instead of assigning it to C, you assigned it to array 6, 7, 8, does that replace 0, 1, or does that create
Nope.
0, 3?
So yeah, you're saying that if we followed one of these indexes and we said this index is now this other array, well, first we create that other array, right? So let's just go down here. And we said, hey, we were going to index 1 of this thing, and we reassigned the index to now be a different reference. We have no way to completely overwrite this thing. we can access this index and go one step further. So like the difference visually, maybe this will help. So look at the difference between 10 and 11. 11 basically went to an index and reassigned the index. It didn't really follow through the reference that was at that index. Line 10 pulled up the same thing. It pulled up the index, but then it actually used it by saying go to dot push. And so this is what actually modified what was at that memory address. Whereas this one says, hey, that index is no longer whatever it was. That index is now this. It didn't follow through. That's the big difference. And you can see here kind of that this does one level deeper. They both selected the index, but only this one really followed the reference to do different work.
So only certain methods that can change the values in the reference.
Yeah, I don't have a way to completely change this whole thing to something brand new. But I can go into it and mutate what's inside of it.
Well, what if you reverse it?
Yeah, we can reverse it. So if we had instead of dot push, if I called dot reverse, we selected the index, which was a reference, then we went a level deeper, pulled this thing up, and reversed it to be 432 instead. Which I know this is a fucking mess up here. Bear with me. If any other array still pointed to memory address 1, when we access it, it would see the change. But we can't really get rid of that whole array and say you're now something else. We can get rid of the indexes that pointed to it. Which gets tricky. We're pretty deep now. So, yes.
Is that kind of like what we need to do with the Sudoku project? Kind of with the nested? Or
No.
okay.
In the Sudoku, you shouldn't really be modifying the board anyway. We just want to read from the board, right? We just want to get sets of 9 numbers. So whatever I was saying before about getting out a subgrid, it's kind of like slice in the way that we're going to write a function that makes a new array called like my little subgrid. And then we're going to have some crazy for loops that are going to go pluck out 9 values and put them in the subgrid array and return that subgrid out. And then we can have one other big array that will hold references to all the different sets of 9 that we just pulled out. But all of those sets of 9 should kind of be their own array that we added numbers to. They shouldn't refer back to the main board. I know that's a lot of semantics though, so that might not have translated well. Hope that helps you.
Yeah, basically. No, that's not. Yeah.
Okay. So big difference, primitives and complex types. It affects how they're passed, how variables are assigned to them. For the 100th time, primitive types just get a value. All the variables just hold values and they have nothing to do with each other. And with complex types, we create them once, we put them in memory, and we give back a reference to where the thing lives. So if any variables want to be the same as a variable that's a reference, well, that takes the same reference. Does reassigning a variable change the data that was in memory? No, it just says you're no longer a reference. You're now maybe a new reference or maybe another string. But it doesn't actually use the reference. To use the reference, we go a level deeper and we can modify stuff there, like push or reverse. So most important when it comes to assignment, am I assigning a reference or a primitive value? If it's a reference, do I want it to be the same reference that I have elsewhere, or do I want a new copy of this thing that I can mess with and not break anything else? Those are like the questions we're going to start asking ourselves when we get more comfortable with this. And for the next few classes, we're going to have functions that call functions and take in functions and return functions. Functions are what? They're complex. So actually any variable that is a function is a reference. And that's what this is building up to, which I guess I'll show you. Last thing, I know today is long. Today is like a really important one. I think that if this isn't taught well, it'll just screw you over in real life over and over again. Because like I have a roommate who's also at a startup and he was a comp sci major. He didn't come through this program. They didn't learn JavaScript. He doesn't know how this works. And I've solved bugs for him and he gets paid more than me. And he doesn't know how this works. It's like, how do you really know what's going on in your code if you just go with what you've kind of seen but you don't understand? So today's a big, deep concept that most engineers might not fully understand. So it's okay to feel overwhelmed right now. I think it's the hardest one in the course. Cool. Equality operators, complex data types compare what? Reference. If it's not the same reference, they're not equal. No difference between loose and strictly equals when it's complex data types. And then what's a cheap way that we can make a copy of an array? But what's wrong with that copy? It's only a shallow copy. Yeah, so we just have to be aware of that for right now, but we're not really going to make you make deep copies of arrays in this class. So just be aware of it. Cool. So the last thing to show you why this is important, I think I did an example of this the other day. So we have a function double num, and double num returns a number times 2, right? Good. So we wrote a little function that takes in a number and returns the number times 2. And map is a function that takes a function. And what it's going to do is it's going to say, hey, I need a new array. And for every value in your old array, I'm going to run this one through that function you gave me. So we passed in a function, right? I defined this function up here. It is a variable. Its name is double name. And I passed in a reference to that function. I told map, I want you to run this function for every number and give me a new list with all of the output from that function. So it takes the 1, it runs it through double number, and it gets back 2. And it gives me a new array that has 2. Then it did it for the number 2, it got back 4, and then it did it for the 3, and I got back 6. So I have a brand new array that has the results of basically translating each of those things through that double num function. Does that kind of make sense, even though we haven't done map yet? So this is called a higher order function, which is what the next lectures are about. They're functions that take in functions. So the reference thing is important there for how the function works. I passed in a reference to this function, but it's also important because we understand that doubled nums, what is this? False. Yeah, I wanted a new array that doubled all of the numbers. And I still have my original, so I can still use both. So immutability played a role here, and knowing how to pass references played a role here. And life gets way easier once we start to use functions like this. Because if I told you to do the same exact thing without the map function, you'd have about 15 lines of code compared to my 1. And that's functional programming. But all of that is coming, and it just shows why the concepts we learned today are important and how they'll be used. Cool. Final questions? Yes?
Does, when you slice your pretty shallow copy, when you spread, is that also a shallow copy?
It is. Spread works exactly the same as call and slice without any arguments. Just says copy everything down here. Only top level, that's it. Okay, how do we feel? Do we kind of have a grasp of it? Are we going to think about, are these the same reference? Are they different? Do I want the same reference? And is this function mutable? Those are the questions we need to think about now as we work with complex data types. Today I did everything with arrays, but this works exactly the same way with objects. I should have done an object version, but it works exactly the same way. You see the curly braces? It means we made a new reference. All right, 5-minute break and workshop.